product of Q trans, Q rot, and Q bi. And so since this is Q trans times Q rot times Q bi, and this is all in the log, I can split them out and write them as R log Q trans plus R log Q rotation plus R log Q vibration. Right? That's what happens when you separate them out into separate log terms. You multiply within the log, you add outside the log. Right? All okay there. This is great except for two pieces. The n sub a. This is not n sub a cubed. If this was n sub a cubed, we would just take n sub a, n sub a, n sub a. This would work very well. You've only got one n sub a, and you've only got this one r. The convention is you always add the n sub a term to translation, and you add the r also to translation. And so by convention, that's where these two missing terms go. So if I just split this into translation, rotation, and vibration, I get this. If I just split this, I ignore the n sub a for a moment, and this, I get this without this n sub a. This n sub a has to go with one of the three terms. This r also has to go with one of the three terms. The convention is to give them to the translational term. And I'll explain why. Okay. So it's just so it's by convention. So you just got to remember, this is what the expression looks like. Stick the n sub a in with the translational term. Stick the extra r also with the translational term. Yeah.
So if you were calculating like S sub trans, then you would have the Avogadro's number and r in there. But if you were calculating like
rotation and vibration, you would not.
Okay.
That's correct. So that's the convention. Why do we do this by convention? If you think about it, just think about entropy. Translation is moving in any of your x, y, or z, forward, backward, up, down, front, back. Entropies due to translation, you'd expect to be much larger numbers than rotation and much larger numbers than vibration. And so the main contribution to entropy is probably translation, and that's why we stick these two terms here. So we stick this term here to make it bigger. The other reason why we stick this term here is, think about the magnitudes of the partition function. Way back when you first calculated this was about 10 to the 30th. Remember? 10 to the 30th-ish. So 10 to the 30th divided by 10 to the 23rd is still a number that's 10 to the 7th. This number is usually in the range of 100 to 200. If you divided this by 10 to the 23, well, that would really suck because you now have a very, very small number here, a negative something, and this would start to screw up the rotational entropy. Vibration, this number is even smaller. It's a number that's probably very close to 1. Okay, and that's why it makes sense to stick these two terms here. So the convention isn't just ridiculous, it's actually really simple. Okay, then. What we're going to do now is calculate translation, rotation, and vibration separately for a molecule, and then see how well it works compared to the third law. And we're going to do this for carbon monoxide. Okay, so what we're going to do is start with translational entropy. Okay, we saw that you can split up your entropy into translation, rotation, and vibration this way. So this is the expression for translational entropy. So for 1 mole of ideal gas, what is U minus U naught trans? What's the thermal energy due to translation for 1 mole of an ideal gas? And we'll also put this. 3/2 RT actually. The entropy might be 3/2 R. If you just take thermal energy, actually I take that back. The heat capacity is 3/2 R because that's the first derivative of thermal energy with respect to temperature. But this is 3/2 RT, right? Since translation has 3 degrees of freedom. Q trans, you probably don't remember right off, but it's in the equation sheet. And so it's 2 pi m/t over h squared, 3/2 times 2. Okay, that was the partition function for translation. Particle in the box, 3 dimensions. Okay, what this means now is S trans, which was, I probably don't need to write this out. S trans, the first term is the thermal energy divided by T. So this is 3 over 2 RT divided by T plus R log all this junk 2 pi mkt over h squared 3 over 2 V. But Avogadro's number comes in with the translational partition function. So I've got now to divide this by x of a plus r. T's here cancel out. This is 3 over 2r. 3 over 2r plus r gives you 5 over 2r plus the same term here. Questions? We are going to do this for carbon monoxide in a bit. Actually, you are going to do it in a bit. But you're going to break up in 3 groups. One group's going to do translation, one group rotation, one group vibration. But let's just go through the other expressions. But questions about this? That's very straightforward. Let's do rotation. So for rotational entropy, first, thermal energy due to rotation. And let's do this for a linear molecule because we're going to do this for carbon monoxide. RT. Should be RT, 2 degrees of freedom of rotation. So it's just RT. And the partition function for rotation, you probably don't have it memorized, but if you have, it should be 2IKT over sigma h per square. Therefore, I can write an expression for S rotation. That's just RT over T, and that's the first term, plus R log 2IKT over sigma h bar squared. These cancel out, so this is R plus R log 2IKT over sigma h bar squared. And what we're going to do is calculate this for the CO molecule. But questions? That's almost straightforward. Finally, let's do vibration. Then we are going to calculate all the numbers, and then we'll vibration and entropy. Thermal energy for vibration.
You all probably didn't memorize this.
RTX over EX to the minus 1. Remember, this was the one that was kind of weird. It didn't follow the classical value, where X is equal to H divided over KT. And the partition function per vibrational mode was 1 over 1 minus M to the minus X. Therefore, S vibration should be RTX over X minus 1 over T plus R log 1 over 1 minus M to the minus X. The T's cancel out. So this is Rx over e to the x minus 1 plus R log 1 minus M to the minus X. And what we're going to do is calculate this for the CO molecule. Okay, you two get translation, 3 of you get rotation, 2 of you get vibration. Oh, actually, I take it back. Since you all are sitting there, the 2 of you get rotation, the 3 of you get vibration. Since it's in the middle, it will make sense.
Lame.
Nah, they will take about the same amount of work.
But it has, what is it?
Right.